Welcome back to the session on turbo emissions. Today we will discuss about the Francis turbine. Francis turbine is a medium head, medium discharge, medium specific speed, radially inward flow reaction turbine. So nowadays for the production of power, modern Francis turbine is used, and it is a mixed flow type turbine in which water enters the runner radially at its outer periphery and leaves axially at its center. So, the Francis turbine combines the radial and axial flow concepts. This Francis turbine mainly consists of four parts. First one is wall casing, or it is also called as a spiral casing. And second one is stationary guide wheel with guide vanes. Third one, runner with moving wheel. And last one is draft. Now let us look at the functions of all these various parts of Francis turbine. First one is spiral casing. So it is an annular channel which receives the water from the penstock. The functions of the spiral casing is to provide a uniform distribution of water around the runner and hence to provide a uniform velocity. In order to provide constant or uniform velocity, the cross-sectional area of the casing gradually decreases as water reaching the runner. That is, the area of the skull casing is maximum at the inlet and nearly zero at the exit. So due to this gradual decrease in the cross-sectional area of the skull casing, it converts part of pressure energy into kinetic energy. And the third function of the skull casing is to protect the runner blades, guide vanes, and other internal parts of the turbine from external damage. And second one is stationary guide wheel with the guide vanes. A series of aerofoil blades fitted on a stationary wheel known as guide wheel. The function of the guide vanes are direct the water onto the moving blades, and second one is to regulate the quantity of water entering the runner by adjusting the space between the guide vanes. And third part of the Francis turbine is runner with moving blades. Runner is a circular wheel on which number of curved vanes are fitted. Water from the guide vanes strikes the curved moving blades, due to which when water strikes the moving blade, due to which the kinetic energy of water is converted into mechanical energy. At the same time, a part of pressure energy is also converted into kinetic energy in the runner blades. So the vanes are so shaped that water enters the runner radially at its outer periphery and leaves the water at the center of the turbine. Due to this, there is a change in the direction of flow of water from radial to axial, which causes the appreciable change in circumferential force, which is the responsible for power generation. The last part is draft tube. It is a conical pipe of gradually increasing area connected between the turbine exit and the tail race. So the pressure of water at the exit or outlet of the reaction turbine is always less than the atmospheric pressure. Hence, water at the exit of the turbine cannot be discharged directly into the tail race. Therefore, to discharge that low pressure water into the tail race, we are using draft. So the functions of the draft tube are number one, it permits a negative head or suction head established at the exit of the turbine, thus making it possible to install the turbine above the tail race. Second one, it is also used to raise the pressure of water at the exit of the turbine by converting the discharge velocity. This discharge absolute velocity at the exit is P2 into useful pressure energy. Hence, the water will be discharged into the tail race. Now let us look at the diagram or figure which indicates the Francis turbine. It consists of a scroll casing or spiral casing. Look here, it's an annular channel whose cross-sectional area is maximum at the inlet and very minimum, almost zero at the outlet. And it also consists of a wheel over which aerofoil section blades, that is called as the stationary vanes, are fitted. Now let us look at the other diagram. It gives a magnified view. Yeah, this is a cut section of the Francis turbine. This cut section part is draft tube, and the yellow color blades indicating the fixed blades are guide vanes, and they are aerofoil in cross section, and this one The red color indicates the runner with the blades. Runner with the blades. Now look here, this is one of a typical runner which is used for the production of power. Right? This is another uh, diagram which represents the runner for Francis turbine. Now let us look at the working principle of Francis turbine. So there are two views here again. One is first angle projection, second one is third angle projection. Shown here. Right. Now the water enters from the penstock at the inlet of the scroll casing of a Francis turbine and it is moves around the scroll casing. As it is moves around the scroll casing, the area of the scroll casing decreases, spiral casing decreases. Due to decrease in the area, the velocity increases. From continuity equation, we know that Q is equal to A into V. When area decreases, velocity increases. Now the water, and let's assume that water enters here. So these are the guide plates. The block color outer wheel shows that it is a fixed wheel over which a series of aerofoil blades known as a fixed blades or guide vanes are fitted. So now the space between these two guide vanes can be adjusted so as to regulate the flow of water over the runner. Now, let us assume that water is flowing and it is flowing between the space of the two guide blades. The function of the guide blade is to direct the water onto the runner and it can also be it also regulates the quantity of water as the space between this so this the space between these two plates are designed in such a way that are adjusted in such a way that it will be acting as a nozzle acting as a converging nozzle as it is moving in the space between the two guide vanes so the velocity further increases. That means to say pressure energy gets converted into kinetic energy here. Now the water possesses both kinetic energy and pressure energy. It moves over the runner blade here. So here as the kinetic energy, the water which possesses kinetic energy strikes the blade here, due to which the kinetic energy gets converted into mechanical energy, which results in rotating of the runner wheel. Then the pressure energy, remaining pressure energy, as it is moving here, will be converted into kinetic energy. So that means to say the pressure at the exit of the turbine is very less, which is less than the atmosphere. That's why water does not discharges or comes out from the exit of the turbine, for which we are using a draft tube here. Now let us look here. The water from the penstock possesses both kinetic energy and pressure energy. Enters here from the top. Enters here. So this is nothing but the guide vane. So now it enters radially. It enters radially around the scroll casing, around the scroll casing, around the scroll casing, and the guide vanes or guides the water over the turbine runner. This is turbine runner in the front view. This is in the top. Let us assume that this is the horizontal position. The shaft of this Francis turbine is vertical in position. That is, orientation is vertical, and this is in horizontal position. Right now, water enters here with a now partial kinetic energy and partial pressure energy enters between the two fixed blades are guide vanes. Here again the space is restricted here. It will be acting as a convergent nozzle. Here the pressure energy is converted into again kinetic energy. This high kinetic energy water strikes the blade, runner blade, which made to rotate the runner blade, which indicates that kinetic energy gets converted into pressure energy. Further, water exposes over here in the runner blade. Again, the pressure energy is converted into kinetic energy. Remaining pressure energy is converted into kinetic energy. At the exit of the runner, the water pressure is less than the atmospheric pressure here. Water pressure is less than the atmosphere. So it is unable to come out of the runner. That's why a conical tube or conical pipe is attached which converts the water pressure that is which is below the atmospheric pressure into high pressure because the area of the conical tube is gradually increases. As area increases, velocity decreases and pressure increases, which increases the pressure in such a way that it should be greater than the atmospheric pressure. Now look here, it is enters radially and leaves axially. Hence, it is called as a radial inward flow. I mean, water enters radially and leaves axially at the center. Leaves axially at the center. This is the function or working principle of Francis turbine. Now, let us look at the velocity triangles and work done equation for Francis turbine. In Francis turbine, as already we have discussed, the water discharges in the axial direction. That is, water leaves the vane at an angle of 90 degree. If the discharge is radial, it implies that absolute velocity V2 is equal to the flow velocity Vf2. That we will see in the velocity triangles. The nozzle angle at the outlet, that is alpha 2, is 90 degree. 90 degree. That is water discharges into the atmosphere at 90 degree. And the velocity of the whirl at the outlet is Vu2, that is 0. Also, in Francis turbine, the peripheral velocity at the inlet is U1 and peripheral velocity inlet at the U2 are not equal because inlet and outlet tips are at different radial distances. See, this is the inlet, this is the inlet, and this is the outlet. So that is diameter of the inlet is bigger than the diameter of the outlet. That's why U2 is not equal to U1 or U1 is not equal to U2. So the inlet and outlet velocity triangles of a Francis turbine are shown here. Now let us look at the inlet velocity triangle. As usual, the water enters at an absolute velocity V1 and it strikes the inlet tip of the blade radially. Radially. So this V1 is resolved into two components. One is horizontal component that is called as a viral component. Other one is vertical component that is flow component or flow velocity. Now the velocity of water flowing over the moving blade is relative velocity Vr1 at an angle of beta 1. This is absolute velocity of the water V1 at an angle of alpha 1. Next, water will leave the blade axially. So due to this V2, that is V2 90, the alpha 2 is becomes 90 degree. So absolute velocity at the exit is equal to flow velocity, wherein the whirl velocity at the exit of the Francis turbine becomes 0. So water exits axially. That is V2 is equal to Vf2 and alpha 2 is 90 degree and Vu2 is 0. Now this is the relative velocity of the water at the exit at an angle of beta 2 and we have only U2. So look at here, this is the tangential velocity of the blade U2. Water is exiting axially, they are 90 degrees. This is 90 with respect to the, so this is the inlet and outlet velocities of the triangle. This is another diagram which indicates the inner radius and outer radius. Now water enters at the outer periphery with a velocity V1 at an angle of alpha 1 and this V1 is resolved into two components. One is horizontal, second one is vertical. And if you could draw a no, tangent here which represents the relative velocity component at the inlet. This is outlet velocity. Look at here. So water is living axially. Water is living axially. That is alpha 2 is equal to 90 degree, which indicates that absolute velocity at the exit is equal to the flow velocity. So which made the VU to become 0. Whirl velocity at the outlet is 0. And this is radial velocity at an angle of beta 2. This is tangential velocity of the runner, the speed of the runner with which it is rotating. Next, let us look at certain design parameters of a Francis turbine. So, the following are the various design parameters that are to be considered while designing a Francis turbine. First one is work done per second by water when it strikes the runner. And it is given by Euler's turbine equation that we know. So, M into VU1 plus VU2 into VU2 plus VU2 into U2. So, here VU2 is 0 because the water exists axially, Vu2 is 0 and alpha 2 is 90 degree. Therefore, this term, the second term within the bracket will become 0. Now we will get the work done equation as W is equal to rho A V1 into U1 Vu1. This is the work done equation. And then since the radius is different, so that's why Peripheral velocity at the inlet is not equal to peripheral velocity at the outlet. Therefore, peripheral velocity at the inlet is given by U1 is equal to pi d1 n by 60 and U2 is equal to pi d2 n by 60, where d2 and d1 are the diameter of the inlet and outlet respectively. N is equal to speed of the next speed ratio. Phi is given by as usual U1 divided by square root of 2gh. And if the phi value is not given, you can assume that it is in the range of 0.6 to 0.9. And next one is flow ratio. It is denoted by Kf, which is equal to Vf2 divided by square root of 2g, where Vf2 is the flow velocity of the exit, and we know the head of the water. Now, discharge through the runner, Q is equal to, as usual, area flow into velocity of flow. So this is at the inlet, and this is at the outlet, right? Next, power supplied at the inlet of the turbine is WQH, where W is specific weight of water, which is 9810 Newton per meter cube. Q is discharge, H is head of water in terms of meters, which gives us in kilowatts. Right. Runner power or work done per second is already we have given that equation that we have discussed as a first equation. And then hydraulic efficiency, as we know that it is a ratio of power developed by the runner to the power supplied at the inlet of the turbine, which is given by work done per second is the power developed by the runner, and power supplied by the runner at the inlet is WQH. Finally, you will get an equation as U1 V1 divided by GH or 2U1 V1 divided by V1 square. This is also the equation which can be used for calculating hydraulic efficiency. Next is mechanical efficiency. Mechanical efficiency, as usual, we know that it is the shaft power to the runner power, or shaft power divided by runner power. So shaft power is P, runner power is, that is work done per second, is given by rho Q into U1 V1. Next, overall efficiency of a turbine, transistor turbine, is given by shaft power, that is last output divided by first input. Shaft power divided by water power, or it is a ratio of shaft power to the water power given by P divided by WQH, or 1000 P divided by WQH if you want to express in terms of kilowatts. Next is velocity of flow through the runner is constant, that is Vf1 is equal to Vf2. And these are the various turbine runners or different runners for different speeds. So this is the inlet velocity triangle for slow speed, wherein the water, this is the inlet triangle for the slow speed runner, and this is outlet velocity triangle for the slow speed runner. So look at the outlet velocity runner. It's velocity triangle. It is common for all the types of runners. But inlet velocity triangle changes. See here, if the beta 1 is less than 90 degree, that is Bu1 is greater than U1. If beta 1 is less than 90 degree. In second case, if beta 1 is equal to 90 degree, then Bu1 is equal to U1. That is, whirl velocity at the inlet is equal to tangential velocity or peripheral velocity at the inlet. Look here. So that is, water enters, okay, your relative velocity is equal to flow velocity. Water enters at an angle of alpha 1, and this is the blade angle at the inlet when beta 1 is equal to 90 degree. Now, if beta 1 is greater than 90 degree, then the inlet velocity triangle will be like this. So that means to say, this is right angle triangle when beta 1 is equal to 90 degree. When beta 1 is greater than 90 degree, it is isosceles triangle. When beta 1 is less than 90 degree, this is the type of triangle. These are the various types of triangles for a different types of runners. So for the different speed, this is slow speed, medium speed, and high speed. Next, we'll come for the multiple choice questions. Now we have few multiple choice questions which are pertaining to hydraulic reaction turbines. First one is, dash turbines are also called as a parallel flow turbines. There are four options. You need to choose the right answer. First one is radial flow, axial flow, radial and axial flow, tangential flow. See, look at the question. Parallel flow turbine. Parallel flow is nothing but what? Which is parallel to the axis. Therefore, axial flow. Answer is correct. Second one is the water from the runner in the reaction turbine is discharged into the tail race through a draft tube which has dash cross sectional area. So draft tube, as we know, is a gradually gradually increasing cross section area. Draft tube has gradually increasing cross section area. Next, third one is which type of reaction turbine in which water flows in radial direction at the outlet and leaves at its center parallel to the axis of the runner. So what we have discussed, that is mixed flow turbine. Modern Francis turbine comes under this category. Next is which type of turbine is a Francis turbine? First turbine, screw turbine, reaction turbine, or turbo turbine? It's a reaction turbine. Question number 5. The overall efficiency of the reaction turbine is the ratio of what? First one is actual work available at the turbine to the energy imparted to the runner wheel. This is correct. That's what you need to do. Now last three answers. Next, sixth question. In a reaction turbine, the draft tube is used to dash to increase the head of water by an amount that is equal to the height of the runner at the outlet above the tail race. This is correct. To prevent the air to enter the turbine. This is not relevant to this. And third one, to increase the pressure energy of water at the turbine. This is also correct. So draft tube will perform these two functions which has been indicated by A and C. That is answer. A and C both are correct. Seventh question. Consider an involved for reaction turbine. Here, water dash flow parallel to the axis of the wheel, enters wheel at outer periphery, and then flows towards the center of the wheel. This is correct. So that's why it is a reaction turbine. Next, for eighth question number 8. In what type of turbine water enters radial direction, leaves axial direction? This is repeated. The answer is a different term. Axial flow. Next, ninth question. Among the following, which turbine requires more head? Pattern that we have already studied in classification of idle turbines. Question number 10. Dash is the difference between head race and tail race. That is gross head. Question number 11. The head available at the inlet of the turbine is net positive suction head, gross head, and net head. Gross head. This is net head. Net head. It is the head available at the inlet of the turbine. Answer C is correct. Next, question number 12. Dash is defined as the ratio between power delivered to the runner and power supplied to the inlet. That is hydraulic efficiency. Next, we look at the next question. Which among the following is not the efficiency of a turbine? Mechanical efficiency, the efficiency of turbine. Volumetric efficiency is also efficiency of turbine. Hydraulic efficiency is also efficiency of the turbine that we have already discussed with the turbine in detail. Next, electrical efficiency. This is not related to the efficiency of a turbine. So, electrical efficiency. Answer D is correct. Correction. Sorry. Next, 15. The ratio of power at the shaft of turbine to the power delivered by the water to the runner is known as mechanical efficiency, volumetric efficiency, hydraulic efficiency, overall efficiency. That is mechanical efficiency. Question number 16. The product of mechanical efficiency and hydraulic efficiency is known as overall efficiency. Next, which among the following is not an efficiency of a turbine? This question is repeated. Next, question number 18. Among the following, which turbine has highest efficiency? Coupler turbine has highest efficiency. Question number 19. Dash is the ratio of volume of water actually striking the runner to the volume of water supplied to the runner. It's volumetric efficiency. Question number 20. Among the following, which turbine has least efficiency? Among the following, which turbine has least efficiency? This turbine. At present, which is the cheapest means of generating the power? Thermal power, nuclear power, hydroelectric power, electric power. So that is hydroelectric power is the cheapest because water is available plenty and cheap. 22. Pipes of largest diameter which carry water from reservoir to the turbine is known as dash. Then start. Now let us solve few numerical problems on transistor bin. Right. Let us look at the problem number 1. An inward flow reaction turbine running at 500 rpm has an external diameter of 700 millimeter and a width of 180 millimeter. If the guide vanes are at 20 degree to the wheel tangent and the absolute velocity of water at the inlet is 25 meter per second, find number 1 the discharge, number 2 the runner vane angles. Look at here, read the problem, understand the problem, list out the given data. So the given data is an inward flow reaction turbine. Inward flow reaction turbine is a Francis turbine. It is a problem on Francis turbine. And it is running at 500 rpm, that is N is equal to 500. And having an external diameter, external is outside diameter, because water is entering from the outer side, outer periphery. So that's why the relevant diameter is, that is corresponding diameter is D1 is 700 millimeter converted into meter. Then width, corresponding width at the outside is V1, that is 180 mm, 0.18 meter. And if the guide vane angle, that is fixed blade angle, is 20 degree, alpha 1 is 20 degree, and alpha 1 is 20 degree. Look here, it is 20 degree, alpha 1 is 20 degree, guide vane angle is 20 degree to the wheel tangent and the absolute velocity. This is wheel tangent, or this is tangential line. The absolute velocity of the liquid. This is absolute velocity. So this is the angle which made between the absolute velocity and wheel tangent, which is equal to 20. And the velocity, absolute velocity of water at the inlet is 25 meters per second. This is the absolute velocity of water at the inlet, that is V1 is equal to 25 meters per second. So by using this data, we have to find out two things. One is discharge, second one is runner vane angle, that is blade angle at the inlet, that is beta 1. So we know that from the peripheral velocity at the inlet, because look at here, d1 is given, n is given, we can calculate peripheral velocity. Since d1 we know, n we know, so u is equal to pi d1 n by 60. We'll get 18.33 meter per second as a inner peripheral velocity. Next, velocity of the whirl at the inlet u1 is equal to, from inlet velocity triangle, inlet velocity triangle. So we have this equation. So V1 is equal to V1 cos alpha. So alpha 1 we know, V1 we know, both are given. You will get V1, that is whirl velocity at the inlet, V1. And velocity of flow at the inlet, that is Vf1. So from inlet velocity triangle, we know that sin alpha 1 is equal to Vf1 by V1, or Vf1 is equal to V1 sin alpha 1. Alpha we know, Vf we know, substitute that. And discharge to the turbine is, to calculate the Vf1, this we have to, right? Q is equal to pi d1 v1 Vf1. D1 is given in the problem, V1 is given in the problem, Vf1 just now we found, substitute them, we'll get discharge as 3.38 meter cube per second. And blade angle or vane angle at the inlet, tan beta 1 is equal to inlet. So that's why from inlet velocity triangle, tan beta 1 is equal to Vf1 divided by Vu1 minus U1. So Vf1 we found, Vu1 we have calculated, U1 we have calculated, substitute them, we'll get tan beta 1 as 1.66, or beta 1 is equal to 58.89 degree. So that's all about the first problem. Now we'll go to second problem. A turbine works at 450 rpm under a head of 120 meters. Its diameter at the inlet is 1.2 meters and the flow area is 0.4 meters square. The angles made by the absolute and relative velocities at the inlet are 20 degree and 60 degree respectively with the tangential velocity. Determine volume flow rate. Second one is power developed. Third one is hydraulic efficiency. Assume whirl at the outlet to be zero. That is, it is axial exit axially at the center of the turbine. Then only and then the outlet whirl velocity is zero. Now read the problem and list out the given data. The turbine works at 450 rpm. The speed of the turbine is given, n is equal to 4. head H value is given, and diameter at the inlet D1 is 1.2 meters, and flow area at the inlet is 0.4 meters square, which is required to calculate discharge. Right. The angle made by the absolute velocity, that is V1, absolute velocity and relative velocity, that the inlet are 20 degree and 60 degree respectively. Angle made by the absolute velocity at the inlet is V1. Angle made by the relative velocity at the inlet is VR1. So this is alpha 1 and this is beta 1. Alpha 1 and beta 1 are given. Right. Calculate the volume flow rate. That is Q you have to calculate. Second one is power P you have to calculate. Third one is hydraulic efficiency. Assume that VU2 is equal to 0. Now from the peripheral velocity V1, we know that D1 is given, N we know, calculate V1. So again from the inlet velocity triangle, we know that cos alpha 1 is equal to VU1 divided by V1, or otherwise VU1 is equal to V1 cos alpha. Alpha 1 given, V1 we don't know, that we will see. Next, velocity of flow at the inlet, that is VF1. VF1 apply sine function, so that is sine alpha 1 is equal to VF1 by V1. Therefore VF1 is equal to sine alpha 1 by V1. Sine alpha 1 into V1. Next, velocity of flow at the inlet, that is VF1. Again, VF1 is equal to this formula. Let's write down as it is. Next, tan beta 1 is equal to Vf1 by Ve1 minus V1. Now Ve1 minus V1 tan is so much of V1. Therefore, velocity of the whirl at the inlet Ve1, velocity of the whirl at the Ve1 is, now we got it as, after simplification, we'll get an equation. It is after simplification of substituting the value of now 60 degree here, we'll get this equation, right? So 1.732 P1 minus 48.97 minus 0.32 P1. Finally, you get P1 as 35.79. Since VU1 is greater than U1, hence modification of inlet velocity triangle is not necessary. VU1 is greater than U1. This is the kind of velocity triangle. Next, peripheral velocity. Now, peripheral velocity U1 is equal to, we know this equation, substitute H value given, you will get U1. Also, peripheral velocity of at the U1. So, from this, you can calculate D1 velocity Vf1, again overall efficiency is much, and volume flow rate or discharge is equal to, is the formula. So, we will width of the bail at the inlet. This is another problem. This is Q is equal to 5.21, power developed is equal to 5272, and hydraulic efficiency is 86%. That's all about the Francis turbine. Now let us look at, or we will glance once again what and all the things or contents which we have covered. Now let us look at recollect the things which we have covered today. Recap. In today's session, we learned Francis turbine and its main parts and also working principle of Francis turbine and velocity triangle of Francis turbine, the expression for work done, and hydraulic equation or hydraulic efficiency of a Francis turbine. Next, design parameters to be used for designing a Francis turbine, and we have discussed around 20 MCQs relevant to the Francis turbine, and we solve three numerical problems, simple numerical problems on Francis turbine. And exercise questions on Francis turbine will be given in the notes or course material. Thank you.